Okay, let's kick this off. Think about this scenario. You're trying to get online, maybe running something important for work, and the main router, the gateway everyone on your network uses, just stops. Dead
Yeah,
silence.
total disruption.
Oh.
That classic network problem, isn't it? The
Mhm.
single point of failure, one device goes down, everything relying on it just stops.
Exactly. And you can't just have everyone manually change their settings, especially not quickly. You need something automatic, something seamless.
Right, some kind of automatic backup plan for that
Mhm.
critical gateway, and that's where redundancy protocols come into play.
Especially when we talk about default gateways on a local network. One of the big ones is VRRP, the Virtual Router Redundancy Protocol.
That's the one.
And that's exactly what we're diving into today. We're looking at RFC 5798. That's the standard for VRRP version 3, covering both IPv4 and IPv6.
Yep. And our mission, really, is to get into the nuts and bolts of this RFC. How does VRRP actually eliminate that single point of failure? How does it keep traffic moving without anyone having to lift a finger?
Okay, so the big problem is that single physical router failing. How does the RFC, how does VRRP approach solving that? What's the core idea?
Well, the fundamental concept in the standard is creating this abstraction, a virtual
A
router.
virtual router.
Yeah, so instead of all your devices pointing to the real IP address of one physical box, they all point to a virtual IP address.
Ah, okay. So it's an address that isn't hard tied to one specific machine. Does this virtual thing have its own unique identifiers then, according to the RFC?
It absolutely does. It has that virtual IP, like we said, but crucially, it also has a specific virtual MC address. The RFC actually reserves specific MP address formats for VRRP.
Oh, really?
Yeah, it's like 0000005E and 0001, followed by the VRRP group ID for IPv4, and a similar one ending in O2 for IPv6. That virtual MSC is, well, it's key.
Okay, so you've got this virtual identity IP and MMC. How do the real routers, the physical ones, fit into this picture?
Right, so multiple physical routers on that same network segment can be set up to participate in the same VRRP group for that same virtual router ID.
Yeah.
And they use a process, defined in the protocol, of course, to elect one of them to be the master router at any given moment.
The master. And that's the one actively handling the traffic for the virtual router.
Precisely. The master router is the one that effectively owns that virtual IP and virtual AMC temporarily.
Hmm.
It answers ARP requests for the virtual IP, but it replies using the virtual AMC. It forwards the traffic sent to that virtual IP.
Okay, so if one's the master, what are the others doing? Just sitting there.
Pretty much they become backups. Their main job, as the RFC lays out, is to listen. They listen for these periodic VRRP advertisement messages that the master sends out.
Advertisements. And how are those sent? Anything special there in the standard?
Yeah, they're sent to specific multicast addresses, one for IPv4, one for IPv6. But the really important bit the RFC specifies is the TTL, the time to live or hop limit for IPv6. It must be set to 255.
255, that's the maximum. Why so strict? What's the thinking there from the RFC?
Ah, that's a deliberate security measure highlighted in the RFC. Setting the TTL to 255 means these packets can't be routed off the local network segment. It keeps VRP communication strictly local, preventing certain types of remote attacks.
Makes sense. Keeps it contained. So the backups are listening for these local advertisements. What's in them that matters?
Key stuff for coordination. Mainly the master's priority value and how often it's sending these ads, the advertisement interval. Priority is crucial for deciding who should be master.
How does priority work?
The RFC gives the highest priority, 255, a special meaning. It's reserved for a router that is the IP address owner, meaning the virtual IP address is also configured as a real IP address on one of its interfaces.
Ah, okay. So if the router that actually owns the IP address is up and running, it pretty much always gets to be the master, right?
Exactly. It has dibs, basically.
Yeah.
Other routers, the ones just acting as backups, use priorities from 1 up to 254. Higher number means more preferred as a backup.
Got it. So backups listening, checking priority. What actually triggers the failover if the master, say, crashes or gets unplugged?
So the RFC defines something called the master down interval. Each backup calculates this interval based on the advertisement interval it's hearing from the master, factored with its own priority. If a backup doesn't hear an advertisement from the master for longer than that interval,
It assumes the master is down.
that's the trigger. Yep. Once that timer expires, the backup thinks, okay, the master's gone. Then, among all the backups that are still active, the one with the highest configured priority transitions itself into the master state.
And takes over the virtual IP and AMA.
Immediately, it starts
Yeah.
owning that virtual identity.
But how does the rest of the network, like the switches and the computers, find out that traffic for the virtual IP should now go to this new physical router?
Good question. The new master, first off, starts sending its own VRRP advertisements.
Yeah.
But more importantly for the devices on the network, it sends out what's called a gratuitous ARP for IPv4, or an unsolicited neighbor advertisement for IPv6. And crucially, it sends these using the virtual AC address as the source. This basically tells all the switches and computers on the network, hey, the device with this virtual MC address is now reachable through my physical port. It updates their ARP or neighbor tables.
Ah, so because my computer was already talking to that virtual IP and using that virtual MC, it just updates its table to point to the new physical path. It doesn't need to change its gateway setting.
Precisely. That's the seamless part. As far as your computer is concerned, its default gateway is still there, still responding. The network infrastructure using VRRP, just rerouting things behind the scenes.
Clever. The RFC also mentions configuring multiple virtual routers, right? What's the point of that?
Yeah, that allows for load sharing in some setups. You could have, say, two physical routers. Router A is master for virtual router 1, and router B is master for virtual router 2. Half your devices use VR1, half use VR2. If both routers are up, you share the load. If one fails, the other takes over both virtual routers. Still fully redundant.
Okay, one more thing. I noticed the security section in RFC 527R8 mentions VRRPv3 doesn't have built-in authentication, unlike maybe older versions. That sounds odd for a network protocol. Why did they remove it?
Yeah, that's a point the RFC authors explicitly address. Their conclusion was basically that VRRP authentication on the local segment didn't really prevent the most significant denial of service attacks anyway.
How so?
Well, someone already on your local network could potentially mess with ARP or neighbor discovery directly, causing problems, regardless of whether VRRP itself was authenticated. So the RFC puts more trust in that TTL 255 check to keep things local, plus good old physical network security.
Interesting trade-off. Okay, so let's sort of wrap this up. The core idea of VRRP, based on this RFC, is creating that virtual router.
Right, a shared identity, virtual IP, virtual MZ address defined by the standard.
And multiple physical routers coordinate using VRRP messages to elect a master who owns that identity at any time.
While the others stand by as backups, ready to take over.
And if the master fails, a backup detects it, promotes itself, takes the virtual identity, and tells the network using that virtual MC, so all the end devices just keep working.
Exactly. No manual changes needed, traffic keeps flowing. It's really a foundational block for building resilient networks, working away silently in data centers, office buildings, everywhere.
It makes you think, doesn't it?
Yeah.
How much of our seemingly stable network connection relies on these hidden layers of coordination, these protocols like VRRP, constantly watching and ready to react so that one little failure doesn't bring the whole thing down?